Okay. Today we're going to keep talking about regression, and we'll go to R and do some regression with a data set. So let's see where we left off. We figured out how to represent a regression model in a matrix form using a design matrix. And working from that and the traditional assumptions of the regression model, that we have IID observations and constant variance. Based on that, we figured out the maximum likelihood estimates of the regression coefficients, beta hat. So we now know for any regression model, under the standard assumptions of IID residuals, how to estimate it, how to estimate the intercept and slopes and all of those things. And we saw that those estimates that result are unbiased estimates. The expected value of beta hat, the vector, is equal to beta, the vector. We also saw that the variance of beta hat, which is going to give us standard errors or standard deviations that we need for inference, the variance of the beta hat vector, the variance of a random vector is itself a matrix. If beta hat has p components to it, then there is a variance for every single component, but there's also covariances for all the pairs. The variance of an estimated beta vector is therefore a matrix, and this is the form. IID residuals, standard assumptions of a regression model. We have beta hat is equal to x transpose x inverse x transpose y. It's unbiased, and the variance matrix is given by this thing. Sigma squared is the variance of the residuals, which we're assuming are constant with respect to x. And all we have left is the x transpose x inverted. X is the design matrix. Okay, so if I wanted to use this result, bottom of this slide, the variances of beta hat are given by this result. I know what capital X is as soon as we get our data, because we know the design of the experiment. We know the first 10 were females, for example, and then they were males. Treatment and control, we know all those things. So X is a known quantity, but sigma squared is not. Sigma squared goes all the way back to our original statement of the model. Y is the response. X is the predictor that's treated as if it is fixed in regression. So that gives us parameters, beta 0 and beta 1 in the simple linear model, but also sigma squared. Sigma squared is an unknown parameter. And we need it in order to get the standard deviations of the betas, because it's right there in the expression. So our next question is, what do we do about that sigma squared? We don't know what it is. It's a parameter. What we generally do in statistics, when we have a parameter that we need to estimate, is we use a statistic. We compute an estimate of our parameter using our data. How could we estimate sigma squared? If sigma squared is representing the deviations about the line, we have this line that we think applies on average, but we have dots bobbing around the line, up and down the line. And according to our model, we can pick up that green curve and slide it up and down the line, and it remains unchanged in terms of its spread, it has the same variance. So what if we took all the deviations from the line, had the fitted line, you have the observed response values, y, and now we have fitted response values, y hat. Y hat would be what you get from model when you plug in xi. So what if we take the difference between observed and predicted, call those residuals, and here's a picture of what it might look like. So x, again, is on the horizontal axis. Now it's residuals on the y-axis. These residuals will be jumping around 0, jumping around y, or residual equal to 0, by construction. Because sigma squared is viewed as constant across x, without respect to x, we can essentially take all those residuals, and since every one of them is equally representative of sigma, regardless of where you are with x, we can just take those and treat them or do with them like a sample variance calculation. If sigma squared is the variance of the residuals, we can compute the residuals and then get a sample variance of them. Sum up the squared deviations from their mean and divide by an appropriate number of degrees of freedom. That looks like a sample variance when we do the sum of the yi's minus y bar squares divided by n minus 1. That's what STATS 101 calls a sample variance. This is just like that. It's just like a sample variance of the residuals. We divide by n minus 2 instead of n minus 1 in the regression context. And the reason we divide by n minus 2 is because we had to estimate 1, 2 parameters to get these residuals. So by estimating 2 parameters, you lose 2 degrees of freedom. In general, for any regression model, we could do this, and we would divide by n minus p, where p is the number of coefficients in the model. Right here it's n minus 2, but more generally it's n minus p. I have that on a later slide. I'll show you that again. Okay, so let's see this same situation from the matrix representation. Our linear model says that y a vector equals x a matrix times beta a vector plus epsilon a vector. And now we know that under the classical assumptions of regression, IID residuals, our estimate of beta is this expression. We know it's unbiased, and now we know the variance and covariance matrix is equal to this. So again, we need to estimate sigma squared. How do we do that? This is just a restatement of what we had. We compute residuals. That's how we do it. If we can estimate the model and get beta 0 hat and beta 1 hat, then we can plug in all of our x's to get fitted values or predicted values, and then the residuals are just the difference between truth and predicted. So here's the same expression from 2 slides ago. This is like a sample variance of the residuals. And we're dividing by n minus 2 here. More generally, it's n minus p, where p is the number of coefficients. Beta 0 is a coefficient, beta 1 is a coefficient, and so on. This ends up equaling what's on the right side of the equality simply because E bar by construction will be equal to 0. The way that we're doing this is we're fitting a line that goes through the middle of the data, and going through the middle of the data is going to mean that the average residual equals 0. Long story short, we can estimate this residual variability, sigma squared, using the residuals. So here's a mess that looks messy, but it's not difficult given what we know now. STATS 101, your textbook would say, when you do simple linear regression, here are the equations for the intercept and the slope. You now know enough to actually derive those in general. Let's just see it in action. Here's simple linear regression model, one continuous predictor variable. Our design matrix for simple linear regression is n by 2, n because there's n individuals, 2 because there's 1, 2 coefficients. And we can write it compactly like this. So square brackets indicating a matrix. 1, that bold-faced 1, is a vector of 1s. That's n 1s in the first column. And the second column is all the x's, x1, x2, dot, 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 xn. So then you can just follow along with these calculations. I'm not going to ask you to do very many, if any, hand calculations like on the exam. But let's just see what happens. When we take, if we want to go about estimating betas and getting standard deviations of betas, we have this x transpose x inverse that we have to work with. So let's compute x transpose x first. X transpose is just put what was the columns as now the rows. So x transpose x is going to be in the first row, first column element, first row of this, dot product with first column of that, 1 transpose 1. First row, second column is first row dot product with second column, or 1 transpose x. If you follow through, you have these other pieces. 1 transpose a vector is equal to 1 times v1 plus 2 times v2 plus dot, dot, dot. 1 transpose a vector, 1 transpose v would be equal to 1, 1, bunch of 1s, v1, v2, vp, which would be the sum. One special case of that would be 1 transpose 1, 1, 1, 1, which would just be equal to 1 plus 1 plus dot, 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 1, p terms equal to p. Back in our slides, x transpose x, then, this 1 transpose 1 is n in this case, because we have n rows. 1 transpose x would be the sum of the x's. X transpose 1 would be the same thing. And x transpose x would be the sum of the squares of the xi's. That's x transpose x. And then you can use the simple rule for inverting a 2 by 2 matrix to get this. X transpose x inverse is 1 divided by the determinant of it times a slightly reorganized version of x transpose x. So if we were to work this through, over here in the second row, second column, that constant times what's out here is the piece we need to compute the variance of the slope parameter, beta 1 hat. This that I have on the bottom is that quantity. So the standard error or standard deviation, same thing, of beta 1 hat would be the square root of n times this constant out front, also times sigma squared hat, because the variance, covariance matrix is sigma squared times x transpose x inverse. When you simplify, you get this expression, and that's what you would see in Stats 101 textbook. Let me just comment on one thing from this expression. What this says down at the bottom of the slide, the standard deviation of beta 1 hat is equal to, so it has sigma hat squared in the numerator, and it has this thing in the denominator. And last time or a time before, we said this expression in the denominator is basically an unscaled variance of the x's. If you wanted a sample variance of the x's, you would sum these things up here, sum of the square deviations from the mean, and divide by an appropriate number of degrees of freedom. The standard error of beta 1 hat is going to increase when there's bigger residual variance. It's going to decrease when our x's are more spread out. What does that mean? Let me go to our whiteboard. If we have a simple linear regression context, x, y, and we're interested in fitting a line. If we had data like this, suppose our data were like that, they're all kind of bunched together. We could fit a regression model and we'd get some slope. If, on the other hand, if we had more points, if we had x's that were further out like this, spread out on the horizontal axis, if there's more variability in the x's, then we would get a slightly different line potentially. When you have, if that's the true relationship, if that line is the true relationship, you will have a more stable estimate of it when you have the x points spread out more. It's easier to estimate the line when you have more coverage on the x-axis. So this expression here gives you some insight into what goes on when you do regression modeling. You're going to have a hard time detecting any statistically significant differences if the residual variability is really high. And or if your x's don't go out far enough. Obviously, if you just had a whole bunch of, if you had n observations at the same exact x value, you could not estimate a line. So to the extent that you can spread the x's out and cover more of the population, you get a more stable estimate of these regression parameters. We care about that because our inferences are typically in terms of regression parameters. All right, now let's think about, we have estimates. We have beta estimates, and now we have a sigma estimate. We are now ready to do actual inference. And I'm going to show you a few flavors of inference with regression. One is a simple test of each individual coefficient, or a test for one coefficient. Suppose we wanted to test in the simple linear regression model or we wanted to test something about beta 1, a slope. Might be, for example, null hypothesis that beta 1 is equal to 0. If beta 1 is equal to 0, there is no slope on average between x and y. If I wanted to test whether beta 1 equaled a particular value, call it beta 1 superscript 0, this is a general form of a test statistic that we can use. And it looks like estimate the parameter of interest, subtract off what you think it is, what you think that parameter is under the null hypothesis, and then divide by the standard error or standard deviation of the estimate. So with beta 1, it looks like this. Estimate beta 1, that's beta 1 with a hat on it, minus the null value divided by the standard deviation of the estimate. This would be called a test statistic. So if I want to do inference and say a hypothesis test, I want to test this null hypothesis that beta 1 is equal to beta 1 0. The way we would do it is to compute a test statistic and then ask, is that test statistic unusual? Is it extreme? In regression, we will compare our test statistics to either a t-distribution or a standard normal distribution. I'll show you that in the example in just a second. That kind of test is only applicable to a single coefficient or simple combinations, linear combinations of statistics. More generally, suppose we have a model that has several covariates in it, and we want to test a null hypothesis that involves multiple coefficients. Then I don't get to go one by one parameter at a time. I need to ask kind of simultaneously, are all of these betas that I'm interested in equal to a particular value? When we have a more generic question in mind that can't be answered with a one at a time statistic like this, we can use what's called a likelihood ratio test. You know what a likelihood is. It's a product of PMFs or PDFs. What we can do in terms of a test is compare two different models. We can compute the regression model that is the one we originally wrote down without making any restrictions about the null hypothesis being true. We could fit our model to the data and wind up with a likelihood. You fit the model to the data, that gives you beta 0 hat, beta 1 hat, and sigma squared hat. Plug those into a normal distribution likelihood, that'll give you L1. The likelihood achieved, the maximum likelihood achieved without making any restrictions. The other model we need to fit is the one where we do make the restrictions. So whatever the null hypothesis is, we need to fit the model that assumes that case. That will give us a new set of estimates, and therefore a new likelihood. And then this expression is a way that we can do inference. This statistic, so if we have those two likelihoods, L0 and L1, then we can compute this lambda test statistic. It's equal to -2 times the log likelihood ratio. -2 times the log of the restricted likelihood divided by the unrestricted likelihood. Under the null hypothesis, if we have a reasonable sample size, or if our data are exactly normal, we can compare this likelihood ratio statistic to a chi-square distribution with Q degrees of freedom. Q is the difference in the number of parameters in the two models. I'll show you an example in just a second here. This just shows the math behind computing the likelihoods. I'll show you how to do it. Let's go look at these data. So weight height data, we've seen them before. Scripts. Okay. Let me load the data in. We have 240 measurements. Here's the first few rows. And let me come down to stuff we haven't seen yet. This just shows the relationship between ANOVA and regression and the t-test. Why don't we look at that real quick? It's good. I think it's good to see when there's overlap between methods. Helps you to understand what they're doing. Let's look at, first let's look at the linear regression model, LM for linear model, treating weight as the response and gender as the predictor. If I fit that model and ask for the summary of it, I get regression estimates. Here's beta 0 hat, here's beta 1 hat. Here's the SD of beta 0 hat, SD of beta 1 hat. Okay. This is equivalent to doing ANOVA. If I wanted to ask, let's test whether there's a difference in mean weight between the levels of this factor called gender. That's also an ANOVA problem, and it's equivalent to the regression problem. This F statistic down at the bottom is, in regression, the F statistic down at the bottom is the statistic for asking whether you can take everything but the intercept out, which is equivalent to the ANOVA null hypothesis. ANOVA would say there's no difference in the means between genders. No difference in the means between genders means I could take everything but the intercept out of my model. Note also that this T statistic is the square root of the F statistic. So from multiple angles, we're doing the exact same thing, whether we do regression or ANOVA in this case. Also exactly the same thing as doing a t-test. Here's that same t statistic as came up in the regression model. Okay. Let's come down to let me estimate. Let me do this real quick. We fit the model between just weight and height. This one right here. That's the one we just did. Let me just define it. So now fit is an object that contains the output. And now let's come down here and manually match. I'm just computing some things that manually match. Let me show you what I did here. So capital X is the design matrix. Capital X is a column of ones and a column of the heights. We have P equal 2 coefficients in our model, beta 0 and beta 1. Beta hat is X transpose X, X transpose Y. The fitted values of the response. If our model says Y equals X beta plus epsilon, then my fitted value, or another way of saying that, yeah, let's just leave it at that. My fitted value would be Y with a hat on top equal to X times beta with a hat on top. Once we've estimated beta, we have fitted values that we can pull out. That's what this is doing. X times beta hat are my fitted values. My residuals would then be the difference between true weight and fitted weight. We can also get that by saying just saying residuals fit. Here's the first 10 of them, and here's the first 10 that I calculated my own way. They're exactly the same. Once we have residuals, here is the estimate of sigma, the residual standard deviation. This comes straight out of the notes. Sum the square of the residuals and divide by n minus p. Sig hat. Let's look at the summary of our fitted object for a moment. What LM calls residual standard error is what we just computed. It's the sigma hat, same thing that we computed. This implements the formula from the notes for the standard error of beta 1 hat, just so we see it's the same thing also, 0.3103, standard deviation of beta 1 hat. Here is the more generic way of expressing variances and covariances of the betas all at once. This is sigma hat squared, that's a scalar, times x transpose x inverse. This is a matrix. On the diagonals are the variances of beta 0 hat and beta 1 hat. So in particular, if I take the square root of second row, second column, I will match the standard deviation of beta 1 hat. So here I am pulling out just the standard deviations of the betas. Give me beta 0, or give me the standard deviation of beta 0 hat, and give me the standard deviation of beta 1 hat. I can do that by using the diag function. That pulls out just the diagonals of a square matrix. On the diagonals are variances, so I'm going to square root them to get standard deviations. .6139 for beta 0 hat and 0.3103 for beta 1 hat. So let's do inference. Let's see what we can do with our toys now. With this simple linear regression model, let's test whether beta 1 equals 0. If beta 1 equals 0, then there is no linear relationship between x and y. One way to do that would be to compute a confidence interval for beta 1. I'll show you more about this soon, but a general form for a confidence interval is estimate the parameter of interest and then go plus or minus some appropriate number of degrees of, or some appropriate number of standard deviations from the estimate. The cutoff tells us how many SDs to go out. And we are going to use, LM uses t-based sampling distributions. This is the 97.5th percentile from the t distribution with n minus p degrees of freedom. So here is a 95% confidence interval for beta 1. Goes from 4.3 up to 5.5. Because it does not contain 0, 0 is not a plausible value for beta 1 at a confidence level of 0.95. If I just wanted to test, is beta 1 equal to 0, that interval right there would tell me you can reject that null hypothesis. If your null value is not contained in a 95% confidence interval, then you know you will reject at a confidence level of 0.05. In other words, the p-value that you would get would be less than 0.05. You know that just by looking at the interval. Here is the t statistic that would apply if we wanted to test whether beta 1 is equal to 0. So I have estimate minus null value divided by standard deviation of estimate. Beta hat is a vector of length 2. So the second one is beta 1. Subtract off 0 because I want to test whether beta 1 equals 0, and then divide by the standard deviation of beta 1. Here is the t statistic, 15.7, and that's the same thing that R spits out by default. When you ask R to do LM, it gives you back this standard type of output that shows you the estimates, the standard deviations, these t statistics that apply for testing whether the coefficients equal 0. You don't have to restrict yourself to that, but R by default gives you these t statistics for each coefficient, is it equal to 0? The column right next to it is the associated p-value. with a t-statistic of basically 16, that's going to have a very, very small p-value. So we are highly confident that beta 1 is not equal to 0 in this case. All right, let's do this too. Here's how you can do a likelihood ratio test. You will be doing likelihood ratio tests in this class. Big picture of a likelihood ratio test is that you need to fit two models, the unrestricted model and the, quote, null model. When you fit them, you pull out the estimated parameters. And then you can plug those parameters into the expression for the likelihood to get unrestricted likelihood and null likelihood. So let's do that here with this simple example. I'll come back to this in a second. Well, no, I'll do it right now. What I want to do, we've already computed beta hat and sigma hat. We have fully estimated the unrestricted model. Now we need to fit the restricted model. So the way we can do that is to ask, first of all, what is our null hypothesis? If we're sticking with what we did just above and wanting to ask, is beta 1 equal to 0? Then our restricted model, if this is our unrestricted model, yi is equal to beta 0 plus beta 1 xi plus epsilon I. And we wish to test null hypothesis that beta 1 equals 0, then the restricted model is the model that would apply if beta 1 was equal to 0. So it's just yi equal to an intercept. Under the null, x is not in our model. This would be the same thing. This is equivalent to y equal x beta plus epsilon, where x is just an n by 1, just a vector of 1s. And beta is a scalar. So beta actually just equals beta 0 in this case. That's what I have right here. The design matrix under the null hypothesis, x sub 0, is just a matrix with 1s in the first column, first and only column. The dimensionality of the restricted model is just 1 because we only have one beta coefficient in the model. And then what happens after that, all of this stuff is exactly the same as what came above, except I'm using the null model design matrix. X transpose X inverse, X transpose Y. Fitted values are X0 times beta hat 0. Residuals, residual standard deviation. So let me run these things. And in order to do the likelihood, we need to compute products of normal PDFs. So I'm going to get normal PDF. dnorm evaluates the PDF of the normal distribution. Evaluate it at the observed data. And use as the mean the fitted values. So here are the fitted values under the null. Here are the fitted values under the unrestricted. The standard deviation under the null, standard deviation unrestricted. I want the dnorm for all my weights, plugging in the respective estimates, and then product those up. It turns out you'll have some trouble if you try to do that exactly the way I stated it, because you're going to have a lot of really small numbers And when you product up a lot of really small numbers, you can have numerical issues. Instead, what I'm going to do, rather than a product of likelihoods, I'm going to do a sum of log likelihoods. That numerical issue will go away if we log transform and sum instead of product. These then are going to be log likelihoods. Log likelihood under the null and log likelihood unrestricted. Then that test statistic that we saw, this guy, minus 2 times the log of the likelihood ratio. That would also be equal to, write it over here, lambda is equal to minus 2 times the log of the maximized likelihood under the null divided by the maximized likelihood unrestricted. That's the same thing as minus 2 times the log of L0 minus the log of L1. And we just computed log of L0 and log of L1. So to compute the statistic, I'm just going to do minus 2 times log L0 minus log L1. That's the test statistic for this likelihood ratio test. And what we compare that to, under the null hypothesis, that statistic is approximately chi-square with q degrees of freedom, where q is the difference in dimensionality of the two models. We have a model that has 2 parameters, that's the unrestricted one, and now we have a model that only has 1. The restricted model has pulled off just 1 parameter. So I want right tail probability evaluated at my statistic in the chi-square with p minus p0 degrees of freedom. It's going to be basically 0 because it's comparable to this test. It's not exactly the same thing. This is a t-test, which is equivalent to an f-test. We just did a different kind, but the one above had, nearly a 0 p-value also. There is another generic form of testing that is more flexible than that one at a time style test. I'll show it to you more later, but this is the slide that it refers to. And in the script, I have code that does this one. This is an f-test. Likelihood ratio and f, those are both valid ways to do inference with a regression model. They're doing slightly different things, though. So I'll skip this for now, but we'll see this example with other data sets later. All right. Okay, now let's go here and start considering a model that has an interaction in it. And let's do inference with our likelihood ratio tests in this context. Instead of just that simple linear regression model that was weight in terms of height, just one predictor, now let's include race and gender. And let's allow for height, the effect of height, to depend on gender. In terms of LM, I can fit this model that I just described as weight modeled in terms of an intercept, a coefficient for height, coefficient for race, gender, and gender times height means interaction. So here's what we get when we do that. And there's a problem here. In particular, the problem is race. Race, let's do table race. Race takes 4 values. These are just placeholders for different races: Caucasian, African American, Asian, I don't know what all they are, but we have 4 different races. The way it's represented in our Excel spreadsheet that we read in is numeric. There are 60 instances of race equals 0, 60 instances of race equal 1, and so on. But those zeros and ones and twos and threes don't mean anything to us. They're certainly not really numbers. It does not make sense to do arithmetic with these numbers. We could just as easily called it 3, 2, 1, 0, or any other 4 unique numbers. So we need to make it clear to R that these are not numbers. When we fit this model, R is treating race like a number. I know that because there's only one coefficient in the model for race. It's treating race as if it's numeric, so there is just a slope in race. That's not what we want. Doesn't make sense to have a slope in a categorical variable. So what we're going to do in R to make sure it represents categorical variables correctly is treat them as factors. A factor to R is a categorical variable. So race, here's the first 10 values of race, just a bunch of numbers. Now I'm going to do race is factor of race. And here's what we have now. It's still the same exact numbers, but notice at the bottom it says levels. That's it saying I recognize that there's only 4 levels of this categorical variable. These are the 4 levels. And it's not going to treat it as numbers anymore. So here is fitting that same model, but using race correctly. And you see you get a different looking output. There's now 3 coefficients for race. What R does by default, whenever you set up a categorical variable through a factor, by default what it will do is take one of your levels of the categorical variable. It'll take the lowest alphanumeric level and treat that as a baseline level to which everything else gets compared. This race 1 of 2.163, that's a mean difference comparing race 0 to race 1, all other things being equal. There are alternative parameterizations of a categorical variable. The one I just described and the default in R is sometimes referred to as a control versus treatment, or treatment versus control parameterization. You take one of your levels as if it's like the control or baseline group, and all the other levels are compared to that one. There are alternative parameterizations. One other parameterization that I'll mention is the sum to 0 constraint, in which case these race 1, 2, 3 could be parameterized to sum to 0. All right. Here is manually estimating this model. Manual estimation begins with design matrix. If you can write the design matrix for your model, you can do all the calculations manually. What I'm going to do to create the model matrix in this case is use a built-in function called model.matrix. Makes it easier when you have several covariates. And what you can do is just say model.matrix and then include what you would have put on the right side of the, or what you would have put as the model statement in an LM call. You don't need the response. You're just setting up the predictors in a particular way. So let me do this and I'll show you what it looks like. This is going to be 240 by 7. Here's the first so many rows. We have a row full of 1s for the intercept. Then we have height, gender. Okay, I'll say one thing about gender in a second, but we have gender, and then we have those race variables. What it's done is treated race, or it's created 3 what we call dummy variables, indicator variables for yes or no, is individual I race 1? If this is 1, then these will necessarily be 0. If this is 1, then everybody else is 0, and so on. Race 1, 2, 3 are indicator variables for race 1, 2, 3. And it did it for us automatically in the model.matrix call. And then the last column is just the product of height and gender. So the first element is 0 because gender was 0. Otherwise, you have the actual height measurements. Okay, with the design matrix, everything else is done as usual. So here are calculations for fitting this model. Okay, so now let's see why a likelihood ratio test is useful. With the model that we have written down, okay, we have an intercept, we have a height effect, gender, race, and also the interaction between height and gender. How would I then test for whether there is a height effect? One thing we could do, or one thing we might consider doing, is testing whether the height term is equal to 0. Is the coefficient for height equal to 0? Let me write this down over here. Our model right now is yi equal beta 0 plus beta 1 height plus beta 2 gender plus beta 3 race 1 beta 4 race 2 beta 5 race 3 and then the interaction. Beta 6 height times gender. So, is there a height effect? How do we ask that? What's complicated about asking that is that height is in the model twice. So if there is no height effect, if height is irrelevant to this model, we're out of time, dang it. If height is irrelevant to this model, then I should be able to take both of those terms out. My unrestricted model is this one. My null model for testing whether there's no height effect would be the one that did not have that or that. To test for height, I'll be done in 30 seconds. Height effect, the null model would be beta 0 plus beta 1 gender plus beta 2 race, and so on. But not the interaction term. Height has been removed. So I'll show you, I'll pick up here next time, but we're thinking about this model that has, we actually have a little more sophisticated one, but a model with an interaction and testing, is there a height effect, or equivalently, is there a gender effect? Either way, we have to worry about two places that things show up. So we're going to have a null hypothesis like this. in terms of multiple coefficients. You can't do that with the one at a time tests that we saw at first, but we can with likelihood ratio tests and F-tests. Okay? See you Wednesday.